Hello people from the future, welcome to Normalized Nerd. Today I'm going to show you how you can implement the linear regression in Python without using any libraries. So why I'm doing this? Well, we know that there are plenty of libraries where the code for linear regression is already pre-implemented, and what we just need to do, we just need to install the libraries, import the modules, and by calling an objects of the classes, you can implement the linear regression in just 2 or 3 lines. But if you want to learn machine learning from heart, you should really need to look behind the curtains, and it is there where the real math magic is happening. Today I'm gonna just try that. So what is my plan here? So in the first portion, I will be explaining the concept of linear regression for real quick, and then I will jump into the code section. Now here's a warning that I'm not going to go very deep in the concepts. My focus would be more onto the implementation part. Okay, so let's jump into the concept. Okay, so what is linear regression? Before that, what is regression? Well, regression is a process where we fit a curve to our given data to predict a value of the output variable for a data point that we don't know. Okay, so suppose we have a data point like this. Here is my dependent variable, and here this is the output variable that we want to know the value of. Okay, suppose we have the knowledge of this data point. Okay, so for at this points we know the x and corresponding value of the y, but for any other points we don't know the value of y, and we want to just find the value of I at every point. Okay, so how can we do it? We can just draw a continuous line such that it fits the data, and by doing that, suppose we take at this point and we just can find the value of y. And in this case, suppose x is some area of plot and y, let's say, its price. Okay, so by looking at this line we can know the price of any plot having any area, right? Okay, so what is now linear regression? Well, linear regression is a regression where this curve is a linear combination of its inputs and weights. In other words, we can write this y, our y output variable y, as a linear combination of the weights and inputs. So what is input? Well, inputs is just this. The independent variables are called as inputs. Okay. And let me look at the equation of this line. So which is just x is equal to mx plus c. And this m is the weight, and frankly speaking we can also regard this c as also weight, but in general we regard this as a bias. But let me add a term x to the power 0, and this is say x to the power 1. So now we can treat both m and c as weights, right? And why it is linear? Because this side contains only the linear terms of the weights. Now remember, in other problems we may have y as m1 x to the power 2, x1 to the power 2, and m2 times x plus c. Here you can see the inputs are not in their linear format. It contains a quadratic form, but the weights are always in linear combination. So that is what a linear regression basically is. Okay, so now to go further, let me erase some of this. Okay, so now we have the concept of hypothesis. So what is our hypothesis in this case? Well, in this case we hypothesize that our output variable is a linear combination of x. How a linear combination? Such that y is equal to w0 plus w1 x. Well, basically w0 and theta 0 are the same, are the equivalent things, and in previous case I just used the letters m and c to differentiate between the weights and biases, but we can generally regard this at w and w1. And in more generally in our code we are going to do this thing by just introducing a vector called w, and it will contain two elements. This will denote our vector of weights. So this is our hypothesis. You can see that this is our linear hypothesis, and what is our job? We just need to find the W0 and W1 such that this line fits our curve in the best possible way it can. Okay, so these are also called parameters, by the way. Now, how we find W0 and W1? Well, to do this, we use a trick called minimizing the cost function. What is the cost function? Well, cost function is kind of a measure which shows us how much our prediction is deviating from the ground truth. By the way, these points that we already know about, these points are regarded as ground truths, and this is our predictions. Okay, so we just take the difference between them. This is called the error, and we square all the errors and add them. And this, the process of squaring and adding, this is called squared error, and the cost function here is called squared error cost function. And you can see the formula here, and this m in the formula is just the number of data points we have. Okay, now we are going to minimize this cost function, and by minimizing this we are going to see which set of values of W0 and W1 minimizes this cost function. Okay, so how we are going to minimize that, minimize cost function? Well, we are going to use the trick of gradient descent. Now, if you are not familiar with gradient descent, then I will highly recommend you to see my previous videos on gradient descent. I will link them in my description. Okay, in this video, I will be just showing you how the necessary mathematical things needed for this gradient descent. Okay, so let me just scroll down. This is our hypothesis that we have just seen, and this yi cap denotes our predicted value at xi. Well, this x is, by the way, our data points. Okay, so this is an array. This is a vector where xi, x1, x2, and as we have m points, we are going to have this much. Okay, and y is basically the dependent values corresponding this input values. Okay, so we can treat them as y1, y2, dot dot dot, ym. Okay, and this I have already shown you that this is our set of parameters or weights, and this w0 is also called as bias, and this is just equal to a c in our first example. Okay, so this is our cost, the squared error cost function. And by simplifying this thing, this turns out, and we are denoting here this as j. Okay, so if you know gradient descent, then you must know that to implement it, we first need to find the partial derivatives of cost function with respect to our parameters. So the parameters we have here is w0 and w1, and it's very easy to find the partial derivatives for this problem. And please turn your calculus sense on. I'm just going to do a little bit calculus. So this was our function, and we are going to differentiate it with respect to w0. And see, first the chain rule is applied, and this turns out as the first term, and as there is no term, that is a 1 is multiplied here, so we are just going to write 1, and this 2 came here, and that's just cancelled out with the 2 in the denominator, and we just left with this cute little formula. Okay, and while doing the partial derivative with respect to w1, here we have xi's multiplied with this w1 term, so this xi will be multiplied here, and again the same thing happens, and this is our second cute formula. Okay, so we just need these two formulas in our code of gradient descent. And now I'm going to just jump into the code. This is the code in Python that I have written in Python notebook that I'm going to explain now. The first thing we need is some data. I am generating the data using a library. Well, I know that I have told that I won't be using any libraries. Well, I am not going to use any libraries to implement the linear regression or the gradient descent, but I have to use some library to generate the fake data. So the library I'm using here is scikit-learn, and from there the dataset modules, the sample generator, we are importing make regression, and by this line we can generate random data. You can see that I have taken 200 samples, so our m is going to be 200, and number of features, that is independent variables, is 1. And these things, the noise, bias and random state, you can change according to your choice, and that will create slightly different data set. Okay, so now an interesting part is to visualize our data. So let me just run this portion of code. You can see that this is how our data looks like. This is the independent variable and this is the output variable y, and we are going to fit a line to this dataset. From eye estimation, we can say that the line should look like something like that, and we are just going to do that. Moving on, we are here declaring our hypothesis. Okay, here I am using the famous library NumPy. Come on, I have to use it for Python. Okay, so as we remember that the hypothesis we are using here is w0 plus w1 times x, the data points. Okay, and this w, as I have already told, is a vector that is an numpy array here, and it contains two elements, w0 and w1. Okay, and one more thing, that x is actually a matrix. So this x is actually a matrix returned by our function, and this y is actually array. Okay, so we are going to access the first element of every row in that matrix, and this is the syntax for it. And remember one thing, here we are calculating the value, the predicted value for each example. And the first thing that might occur to you, that why I'm not using a for loop here. We can just use this using a for loop, but that would take me a really long amount of time, and that would reduce our efficiency. So this format is called a vectorized format, and this really speeds up our process, and which is very important in machine learning. Moving on, this is our cost function. Well, our cost function takes three arguments: w, the weights, the matrix of features, and the y, the ground truth outputs. Okay, so from the formula, you remember that we are using a squared error formula, and that is half m, half 1 by 2m times this whole thing. So this 8xw minus y, this is basically the differences, and then I am squaring all the differences, then I am taking the sum of the array. That gives me the cost function that we are denoting here as j. Okay, now we are going to enter into the gradient descent. The first thing we need is the partial derivatives, right? So we are going to calculate the partial derivatives from this grad function. It takes three arguments again: the weights, matrix of features, and ground truth outputs. Okay, so in this function I am declaring a array containing two elements, which is g, and in the first element of g I am storing the partial derivative with respect to w0. Okay, the partial derivative of the cost function with respect to w0. And if I just go back and show you the formula again, so this is the formula that we are calculating here. And similarly, in the second element of g, we are storing the partial derivative of our cost function with respect to w1, and we are just returning the g. Okay, so now the most important function, that is the descent function, where our iterations are going to happen. You can see it takes three arguments: w new, w prev, and wr and lr. This is just learning rate. Okay, and again I'm saying you, if you want to know about gradient descent in more detail, please check my previous videos on this topic. And please don't worry about the code, because you will find the code in my GitHub repository, and I will definitely link that in my description. Okay, so the first thing I'm printing here, the current value of w prev. Well, w new and w prev I'm just using to updating the value of w. and in the first iteration that I'm initializing a w, and that is what I'm printing here, and also the corresponding value of the initialized value of w. Okay, now the variable j actually keeps tracks of the number of iterations. Well, you know that in gradient descent we almost never gonna find the actual minimum. We actually had to terminate at some point. So that to keep track of the number of iterations, we are just using j. And now we are entering our while loop, and the first thing we do, we update the w priv to w new, so that it contains the current value of w. Okay, now this portion is very important because here I am declaring two temporary variables, w0 and w1. Why? To perform the simultaneous updates. Okay, so in w0 I am storing the updated value of w0. Okay, so this is just w priv 0 minus learning rate times partial derivative of cost with respect to w0. And similarly in w1 the same thing replaced by just 1. And at this point I have got the updated value of w0 and w1. Now I am just going to update our w, that is w new equal to the list w0 w1, and this is the step where the simultaneous update is happening. And then I'm just printing the w new and the corresponding cost. Now we have to terminate our process of iteration at some point, and the criteria I'm using here to terminate, one criteria is that if the distance between two corresponding w vectors, and I'm using the 2 norm here. If you're familiar with norms, and you can easily spot that is the formula of 2 norm, and is the 2 norm between the w new and w priv becomes less than 10 to the power minus 6, then it just returns our w new. Okay, and in other case I am having, if the number of iterations crosses 500, we are also terminating the thing. Okay, and here's the j is incrementing after every iteration. Okay, so we are done with gradient descent. Now the thing we need to do is to initialize our parameters, because of course we have to start at some point, right? Now I am just blindly guessing that 0 and -1, and then the moment of truth, that is the training our model. And you can see that our gradient descent is actually working, and see at each step our cost is decreasing by a little bit. And if I just move down, okay, so this is the final cost that it finds, and this is the corresponding parameters. Now the coolest part, we are going to visualize the results. Okay, so what I'm doing here is that we have got our parameters, that means we have got our weights w0 and w1, and we are going to define a formula to draw a line which returns the w0 plus w1 times x, and this is a graph function which just plots the graph, okay, the linear graph. So this is just the basics for plotting the whole thing, and in this step I am just plotting the scatter plot that I have already plotted there. So this will be plotted first, and after that I am just plotting the line. Okay, so let me just run this, and voila, just look at here. This was our data points, and this is our linear curve that fits the data point, and it looks pretty good. And actually it is good, because one thing I should mention, that the error function that we have used here was a square error, which is a convex function. What does it mean to have a convex function? It means that it has only one global minimum all or global maximum. In this case it has only one global minimum, so our gradient descent will always converge to that minimum only, and it has done that, and it has found this line. So that was all for this video. I hope you enjoyed this video very much, and please like and share this video, and please subscribe to Normalized Nerd, and thanks for watching.